Okay, so before we get on to our next section, the question burning in your head right now is, okay, I get x and y. I've been dealing with x and y for a while. Show me something new, right? What if there's a third variable? What does that do? How does that affect things? Did I create some new dimension? Did I just blow your mind? My mind is blown. This leads us to parametric equations. So today we're going to look at understanding parametric equations, how to graph them, how to convert from parametric to rectangular, and from rectangular to parametric. First, let's define a few things. So, parameter. The parameter is the third variable. So that's what we're talking about when we say parameter. Parametric equations are sets of equations in terms of the parameter. Or set, I should say. Set of equations in terms of the parameter. The plane curve is the resulting path of parametric equations. That's a really fancy way of just saying it's the graph. And the orientation is the direction of the curve for increasing values of the parameter. Now, all of this sounds like we're doing something incredibly new, maybe, but really we're not. It's just going to be graphing functions and relations that you've seen before. The only difference is we have this third variable, and the third variable gives us direction to that curve. Whereas before we might just have a line or a parabola or some other sort of shape that we're used to seeing. Now there's direction to that line or parabola or other shape that we're used to seeing. So let's look at the parametric equations. So here I have parametric equations: x equals t squared minus 2t and y equals t plus 1. The parameter is t. It doesn't appear on the graph of the curve if we were to graph these, which we will in a minute. I won't spoil that, but it won't appear on the graph, except it gives direction. So the x-coordinate of the point on the curves are given by the function x equals t squared minus 2t, and the y-coordinate of the points on the curve are given by a function y equals t plus 1. So this is similar to plotting a vector, which vectors we know can look just like our normal functions and relations as well. With vectors we have I and j components. Here we have the x and y component. T, or the parameter, usually gives direction to a curve, so the curve can represent a path over time, or it can represent a path as an angle changes, or as some other variable is changing. Alright, so now let's get into sketching the curve represented by the parametric equations, and we want to indicate the direction of the curve. There's two main ways to do this. One way is to eliminate the parameter. Eliminate the parameter. This is a fancy way of saying convert to rectangular. So it's converting the parametric equations into a single rectangular equation. The easiest way to do this is to take one of the equations and eliminate the parameter. So for this example, I'm going to say t equals y minus 1. So now I know, x equals y minus 1 squared minus 2 times y minus 1. Now in this case, I can see that this is going to be a relation, not a function, which I could still graph. This is going to be a sideways parabola. And I can plot x and y values and graph it that way. The other way to graph a parametric, though, because that's not a simple function for me to graph necessarily, is to just make a table with the parametric equations. And since I would be basically making a table with the quadratic relation, I might as well just do the table with the parametric relations, or parametric equations. So now, when we do this, we're going to have t, x, and y. And for this example, we'll start with t equals 0. And we'll go down to 5. So I want you to go through and fill out this table and then plot these points. And we'll see what the curve comes out to be. So pause the video, fill out the table, and unpause when we're ready to look at the curve. Okay, so our curve should look like this, based on the values that I plugged into the table. Now I chose to start at t equals 0. You could start with t being negative values, and then the parabola would have continued on down in this direction. But now we can see that there is a direction to the curve as t increases. But otherwise it's just plotting points of, in this case, a relation that we've seen before when we did conic sections back in AATH. So in general, we can see as t increases from 0, x first decreases but then begins to increase, and y is going to continue to increase forever. And we can see that, or we could have seen that from the equations. Alright, so now I want you to try this one. Sketch the curve represented by the parametric equation, indicate the direction of the curve when x equals the square root of t and y equals 1 minus t. Do this by eliminating the parameter. Pause the video, unpause when you're ready to check your curve. Okay, so our curve should be going down. That's the direction of the curve. I got that from doing this table. Now here, what I want to talk about specifically with this problem, so if we eliminate the parameter, there's two ways in which we can do that. So what I did on the left here in the green versus what I did on the right here in the blue. And when we eliminate the parameter, we need to be aware of the domain of t. So that's what I wanted to specifically point out with this problem, is if I look at the x parametric equation, the domain of t, although it's not stated here, is t has to be greater than or equal to 0. So that applies to everything. So if I eliminate the parameter by solving for t in the x equation, I get t equals x squared, but I need to recognize t has to be greater than or equal to 0. So when I substitute that into the y equation, that means x has to be greater than or equal to 0. So if I use this version of the rectangular equation, then I have to understand I'm restricted to x is greater than or equal to 0. However, whereas if I do this version, so if I solve the y equation for t and then substitute that into the x and leave it in this form, now I don't have to worry about that as long as I leave it like this. As soon as if I tried to square both sides and solve this for y, then I have to pay attention to x has to be greater than or 0. Greater than or equal to 0, sorry. So I used this equation here and I plugged in y values to get the x values. Next one, same thing. Sketch the curve represented by the parametric equations and indicate the direction. Pause the video, do that, unpause when you're ready to check your work. I'll give you a hint, pick values that are nice for cosine and sine. Oh, one thing, I want you to eliminate the parameter here, but you don't have to graph it by eliminating the parameter. It's actually easier to graph by just plugging in values to the trig functions. Alright, so our graph should look like this here, where my starting location is at the point 1, 0, and then I just kind of go through this cycle and it'll continue on forever as theta grows. So where do I come up with that? Well, I did a table over here, so I did theta is 0, pi fourths, pi halves, 3 pi fourths, pi, and then I stopped there even though that's actually only half of the graph, because I know from there I can figure out the values for 5 pi fourths, 3 pi halves, 7 pi fourths, and 2 pi. So I could see the pattern at that point. Now, eliminating the parameter here. So that's how I came up with the graph. What about eliminating the parameter? Well, first I looked at y equals 2 sine 2 theta. Well, sine of 2 theta is 2 sine theta cosine theta, so 2 times that becomes 4 sine theta cosine theta. But what's cosine theta? Cosine theta is x. So I substitute in the x. Now solve this for sine of theta in terms of y and x. So sine of theta is y over 4x. Great. Now we want to use our trig identity. Sine squared theta plus cosine squared theta is 1. We know cosine theta is x, and we know sine of theta is y over 4x. So this becomes y over 4x squared plus x squared equals 1. Now just do a little bit of basic algebra and I get y squared equals 16x squared times the quantity 1 minus x squared. So that is how we can eliminate the parameter with those parametric equations. Next thing, I want you to find a set of parametric equations to represent the graph of the given rectangular equation using the parameters for a, t is x, and b, t equals 2 minus x. So how do we do this? Well, the first one, here is your x relationship. So you know x equals t, and then you know y equals 6t squared minus 5, because I did a substitution for x being t. For the second relationship, we know x equals 2 minus t, and we know y equals 6 times 2 minus t squared minus 5. So if we multiply this out and simplify, we get y equals 6 times 4 minus 4t plus t squared minus 5, which leads us to y equals 19 minus 24t plus 6t squared. So those are our parametric equations. So going from rectangular to parametric, you have to be given some relationship between one of the variables and the parameter, and then you just do that substitution. Okay, so why do we use parametric equations? We use them to describe curves in a plane when one function just won't do. Because it allows us to describe a specific path, because it can give direction. We can plot points for various values of t, being careful to notice what the range and the domain of t should be, and then to convert back and forth we can eliminate a parameter or substitute in. We will look at doing these on our calculator as well, because our calculator can do parametric equations for us. So converting from parametric to rectangular, just make sure we solve one equation for the parameter and substitute it into the other equation. Check the domain of the original as well. That can be very important. Lols.